Hello everyone, it's July 21st, 25th. First things first, let's take a look at this. You see that? You see that this morning? Finally got it. Well, like I said yesterday, I took a look at the discussion, not seeing the solution, but just look at people's title and learned that this was a Amazon online assessment. So I was like, I have to get it done. I have to get it done. And well, I did. It's definitely not the best solution because you see the time. It's not really fast, but I'll go through this one more time. Just kind of help myself think through. It's and overall, it's not that complicated. Yeah, you know what? It is complicated. You see, I have prefix sum. I have two. I thought it need three, but actually two. I have two prefix sum, one monotonic stack, and a bunch of oh yeah, monotonic stack. And actually inside the monotonic stack there is another prefix sum. So yes, it is three prefix sums. But man, isn't that something that's made me feel very nice, very good. But anyway, we're gonna hit this one first and then go for the other thing. So what is this? Lowest common ancestor of a binary tree. Given a binary, find the lowest common ancestor of two given nodes in the tree. The definition is the lowest common ancestor defined between two nodes P and Q as the lowest node in T is a tree that has both P and Q as descendants, where we allow a node to be a descendant of itself. So if I want to find 5 and 1, that would be 3. If I want to find 5 and 4, that would be 5. And I want to find 1 and 2, yeah, that will be 1. All the values are unique, and the P is not equal to Q. Both exist in the tree. Okay, so if I want to find a common ancestor of this node and this node, how do we approach that? Well, to find a common ancestor of these two, is that the same as finding the common ancestor of their parent? Does that make sense? Well, that does make sense, but or maybe we can, I don't know, like, because a common ancestor, there has to be descendant, right? So we can traverse and then we can find all the nodes along the way when we get to this. So we need to search. We need to search for, and then we have a path, right? And we can compare the two paths and then see where they first diverge. Now that is a method. But I feel like, because it's a tree, there gotta be something smarter than that. Maybe BFS is easier. I don't think so. Yeah, I'm more and more in favor of the method of just traversing the thing. To find a path that leads to the node, and then find the last one that they're the same. That will be O log n. Oh, hold on. That's not O log n, that's ON. ON to find both. We can be like on the same. We can do 1 to find both, right? And then we can make that into no better way. So if I'm looking at myself, I'm looking at a node. The question is, am I the common ancestor of those two nodes? That's what I want to learn, right? How do I learn that? I just go to my left and go to my right to see if the node is in one of the subtrees, right? If both return true, then I am an ancestor, right? Then I am an ancestor. Okay, so we keep going this. So everybody's trying to ask. Everybody's trying to ask. And the first one that will return true. But the first one that will return true, I mean, what I can do, I can say it's 5 in it, and is P in it, or is Q in it. Okay, is P in it and is Q in it. Can return, let's say, I'm gonna take the 1. Yeah, I can do those tricks. And then I can all them. Okay. So in this case, I say 3, right? I want to see if, so I go here, so I have 5. I want to find if 5 or 1 is in the subtree. And then what 5 is, then I need to say if 1 is, so I traverse here, traverse to find if 1 is. 1 or 5 is. So this will return 0. This one will return 0. And here will return, let's say, return 1, 0, return 2, right? And here, because this one I got 0, I got eventually is 1, 0. So that's no good. So this will be the first one that receives a 1, 1. Now how do I determine that this is the first one that receives a 1, 1? Because I go from the top down, right? I always go left and right. So I go left, left, left. Well, to put another way, because I am going DFS, right? I go depth first. If I traverse that doesn't have it, then this doesn't have it. If I'm on a branch that does have it, right? That does have it. Then the first one that gets hit is the first one that gets hit should be. Because no matter where they are, the first node that gets both ones is the lowest common ancestor. And I can fill that up. And then we have to rewind the entire thing. So yeah, I think Yeah, I think the first one that got both is the correct one. Not the first one, if I have one that gets both, and that is the correct one. I think this makes sense. Okay. Yeah, I just don't want to do it the other way. I don't want to do it. Oh, hold on. Did I do it yesterday? 24. Yeah, I think I did it yesterday. Yeah. Basically, I don't want to use the method where we find the two paths and then just compare the two paths, because I feel that method is kind of stupid. I don't like it. I want to use something better. Okay, so what we're gonna say is answer res is none. Okay. Walk into self.res and then dfs node. It's gonna be tree node, and this one will return an int. All right. So what do we do? What we're gonna do is, I want to see if this one will say if not node. Okay. Then we'll return. Oh, we're gonna have option here. So it could be. So that will return 0. Right. Otherwise, I'm gonna say L equal dfs node.left, right equal dfs node.right, and current will equal to L or R or how do I do myself? P. If I'm equal to P or if I'm equal to P or equal to Q. If I'm equal to P, so I say node.val if it's equal to P, right, then it's going to be 2. If else, if node.val is equal to Q, else is going to be 0. This is going to be 1, right? When you say if current is equal to, that's 3, right? If equal to 3 and self.res is none, self.res equals node, turn current. And then we just run dfs, basically go through the entire thing, and then return self.res. Let's see. See if this one works. Nope, does not work. Huh. Why? Or if it's equal to P, if equal to P, I will or 2, which is 1, 0. If or else, if it's not equal to P, we'll say if it's equal to Q, then I will, that's 0, 1. Or else, which doesn't equal to both, will be 0. That's very interesting. Hold on. Why? Print current node.val. Current is always 0. This is or, right? Wait, I might have the syntax wrong. Hold on. 1 or 2. Yeah. I mean, 6 is 0. 7 is 0. That's understandable. But 5. How 5 is 0? Note the vowel is equal to. I shall return 2. The heck? Or 2 if, yeah. Hold on. If note the vowel is equal to P, I'm going to print L, R, 2. Hmm? What? Oh! You gotta be kidding me. You guys, come on. You guys, come on. The heck is this thing? Alright, the heck is this thing? P and Q are tree nodes. This is ridiculous. Alright, I shouldn't say it's ridiculous. It makes sense, right? They say the 2 nodes. They say these are 2 nodes. I just thought they are values. Okay. Okay, that's fine. Yep, I think this shall cut it. Oh, I didn't try the... I didn't try the other thing. But the runtime's terrible. Absolutely terrible. Alright, so first of all, this is not the vowel. It's this. Your runtime's bad. 236. ON. But honestly, it's very slow. For I don't know why. I mean, we can try the other solution, which is, you know, a stupid solution. We can just look for it. All right. Say def search. Target is going to be a tree node, and we have a node. The option tree node, and I have a target. We're going to return a path. No, we're going to have a path. No, I don't really think this is smart. Okay, I'm just gonna say, I'm just gonna see what type of solution I have. I feel this is easy enough. Huh, we have like 4 different lowest common. 31 test cases. What is a smarter way in this? left to right, found self, larger than 2. That's almost the same as this one. Found left, found right, found self. That's true. Like for me, I just use these number values, right? I say this is the left value, right value, just how is, but instead of plus it into larger than 2, what I do is 1, 1 means we find both, 0, 1 means we find Q, and 1, 0 means we find P. And the current is just do what we have. And if it's equal to 3, then we find, yeah. So I think it is the same. I don't know why this just becomes so slow. I can actually mention it. So the return value, right? The return value of DFS is 1, 0, 1, 0, 0, not found. 0, 1, found Q. 0, 2, no, 1, 0, found P. And 1, 1, found both. Thus, the check is for 3. Okay, let's just call that. Now I'm gonna go back to this one. All right, so let's write this out. I think give example. 1, 3, 1, 4, 4, 5, 2. Okay, so the idea, right? The ideal is as we go, if this one is smaller than whatever's in here, then these will be popped and I will stop by this. Okay, so we need to first figure out all the subarray that's ending in 2 but after 1, so like 5, 2 and 4, 5, 2. So we need a faster way to calculate 2 plus 5, 2 plus 4 plus 5 plus 2, because they will all be based, they will be all multiplied by 2. Now, to do this fast, we can use prefix sum, and the method I think about is we're going to right to left, right? So the first element is 2. Second element is 2 plus 5. Third element is 2 plus 5 plus 2 plus 5 plus 4. You see what I'm doing here? So I'm just building this up. And let's do one more. 2 plus 5 is the next element. 2 plus 5 plus 4 plus 2 plus 5 plus 4 plus 1. Okay? So if I want to find 1, 4, 5, like I want to find, so if I want to find 5 plus, let's say 5 plus 4 plus 5 plus 4 plus 1, what I do, I go look for this value first. Okay, so if I do this value, this whole thing, and minus, so this value is 1, 4, 5, 2, right, altogether, and a minus 2. Well, actually not minus 2, minus 5, right? Minus 5. Yeah, was it minus 2 or minus 5? We want, no, minus 2, my bad. So I want to find 1, 4, 5. So what I do is I get a value of 1, this one towards the end, which is this, minus 2, right? So this will give us, this thing, right? Give us this thing. Will give us this thing. And then to compare this and this, we can see the only difference is everything has a 2 attached to it, right? So we just need to minus, so this thing, minus 2 times the length of this, and that's it. So that's how we can get this triplet, or the sum of this triplet. So again, I need to build a prefix sum from right to left that's built like this. So each one will add to the previous, and then we also need a running sum along the way. And then if we want to find any segment, it's going to be the value at this index minus the value at this index, right? So after that, we need to minus the sum of the extra, multiplied by the count of this. So that's what it is. You see the first PS. Yeah, we can do this. All right. So step 1, build a prefix sum that allows us to compute the sum of all subarrays, and in range ij that ends in strength I in O1 time. To do so, we go from right to left to build a prefix sum, which is called psum1 in the solution. Yeah. Once we have the step 1, right? And then step 2, build a regular prefix sum such that we can compute the sum of range I to j in O1. This is psum2. Okay. With psum1 and psum2, the sum of all the subarrays in I to j ending in strength I can be expressed as psum1 I minus psum j plus 1. So that's the middle, and then we have to minus times, I think it's j minus I. Actually, j minus I plus 1. That's the total number. And this is going to be psum2 minus 1, because we always go to the end, minus psum j, minus psum j. So that is what I call the between sum. So we can see we have a s between. It's a between sum. It's psum1 minus psum j plus 1. Of course, we have to handle some indices, and minus psum2 minus 1 minus this times this, right? So this is the between sum. So that's the 2 steps, so we can get that. So once we have that, we are able to pop everything and calculate whatever is inside here, and they were ending at 2. So we have that. That's like the first part. Now the second part is how to do everything to the left. Now, we already dealt with it because we know the contribution from this position, right? So like when we pop this, it's going to be like this, right? So we know the contribution from here. Now the contribution from this one is going to be something ending in 1. I shouldn't say 1. Let's call it this. Let's call it A1, A2, and A3, right? So A3 is currently what we are at, and then let's call it dot dot dot. We don't know how many is it, but we have A2, right? And now we know along the way there's A1 there. Okay, we can actually also say along the way there's also A0. So these are all smaller. So just what happens for A2, we know the contribution of A2, and contribution of A2 equals to whatever ending in A2. Right, so A2 plus something multiplied by A2. But once we reach A1, because A1 is smaller than A2, So they were based on A1. So it'll be from A1 to A2, something to A2, all the way. They were all based on A1. And now it hit A0, which means from A0 to A2, something, something. They were all based on A0. So the contribution, or what I call it, is a DP, right? We call it DP. Say DP2 is going to be A2 times, let's call it subarray. S1, S2, subarray S1 plus S2 plus S3, okay? And then plus A1 times subarray S1, no, that is 4, is 5, right? And then plus A0 times S6 plus S7 plus So that is how DP2 is. But now we say, what about they ending at A3? Now we calculated something already, right? So for A3, for remaining, that's starting from A2, what we'll see is the remaining, we can say the remaining of DP3 is equal to from A2 to A3, right? So we have a length S in between. So it's going to be S1, right? We're going to say it's be A2 times S1, so whatever is here, plus the in between, I call it S, right? Plus S2, whatever is this one, plus S, plus S3, plus S, plus See that? Plus A1 times, so A1 will be A1 to A2, that's S4, plus S. So it'll be X4 plus S, plus S5 plus S, plus right? Plus A0 times S6 plus S, plus S7 plus S, plus right? And we can simplify this, right? We simplify this. What is this one equal to? I should put equal here. Right? This is equal to A2 times S1 plus S2 plus Actually, let's just don't go S3. It's too many things. Yeah, let's not go S3. Right? Plus whatever there's a count, right? Because we're just repeating S. So A2 times some count, it's called count 2 times S, plus A1 times S4 plus S5 plus plus A1, count 1 times S, and plus A0 times S6 plus S7 plus plus A0 times, it's called C0 times S, right? And now we find out that this thing plus this thing and plus this thing is exactly the same as dp2. You see that? Same. So is this equal to dp2 plus, and then we can take s out. S times a2 times c2 plus a1 times c1 plus a0 times c0 plus, and actually we have more going on, right? So a2 is just this value. A1 is this is actual strength, and this count is the number of elements in between. You see that? There's a number of elements in between because the count is how many subarray that ending on A2 but doesn't include A1, right? So this is just the index, the difference of the index between this and this. Simple as that. So for A3, I need to know the sum of this, but we don't have to calculate the sum every time. We can just put this as a prefix sum, right? Because for A2 is going to be require A1 times C1 plus A0 times C0. So when we do A2, we just add another one, and then we push it in, right? And then for A3, I can just look at A2. So all A3 needs to know has been included in A2. Part of it is the DP, which is the actual contribution, and part of it is going to be the stack, the monotonic stack, and the information is in there. So that's what we're doing here. We say the stack is going to be including index and the prefix sum of count times value. So I'm going to actually include that one here. So step 3, right? We need to find, we use a DP array to keep track of the contribution. I spelled wrong. The contribution from strength I, from strength I that counts all the subarrays that end in strength I. We can compute dp I from dp I minus 1 and a monotonic array. For instance, let's say we have a monotonic array. I'm going to just put this one here, right? Where A0 smaller than A1, smaller than A2. Now we have A3 coming in. Well, actually, it's going to be like this, right? A3 coming in. It first pops everything out until A2. All the popped elements, on all the elements between A3 and A2 can be computed using the method in step 1 and 2 to find their contribution based on A3. Now, with A2, we know, right? We know dp2 is equal to, let's just copy this. dp2 is equal to this. Right? Say where S1, S2, are subarrays ending in A2, A1, and A0. Let's also assume that the subarray between A2 and A3 ending A3 has some S. This can be computed, right? Computed from Psum 2 in O1. Then we can write dp3 is equal to, right? dp3 is equal to this thing. Equal to this thing, which is equal to this thing, which is equal to this thing, right? Thus, we just need to use yet another prefix sum to keep track the value of this thing. And this can be done in each element of the monotonic array. So that's for this monotonic array, right? We have this and this, right? So for every element, we say if this is larger, basically this is check, if it's empty. Yeah, we will put something here like a dummy value. And if it's larger than 0, which means we'll have something in there, and if the current strength is smaller or equal to the strength that's in at the end of the stack, then we're just going to pop the stack, right? We pop, 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 until we cannot pop anymore. Then we need to find the sum in between. So we use step 1 and step 2. We talk about it, so we compute this. Now the only complicated part is here. If the current one, if it's the last, right? If the current one is the last in the strength, if the current one is last in the strength, then when we do minus, it's just minus 0, right? We don't have any p sum because we're already at the end. Like I plus 1 does not exist, so we have to just minus 0. So basically we take the entire thing. And then minus, this is easy to understand, and times, say I plus minus the previous index. So we get an S between, and then we get our first dose of contribution with S between times the current one, because current one is the smallest for all those in between. And then we say if there's something in the stack, then we can use that dp, you see, that dp thing, plus, so we need to plus this s. Now how do we calculate the s? And we use the p sum 2 to calculate the s, which is the sum of the values, all the values in between the myself right now and the end of the monotonic stack. So we find the sum multiplied by this. This is just the pre-sum time of count times value. So we times that, right? We have this plus we know this, and we times this. So this is a prefix sum inside the monotonic array. And then we get the dp, right? We get the current value, and then we simply just append the new thing, append to it. It's going to be this is the index, and then because we have to do the prefix, so we have the previous one and plus the current strength times count. Count is I minus the previous one. That's the count. So we update it, and then boom, done. It's a good problem. Took a long time to solve, but I feel very good that eventually was able to, make this happen. We are going to, of course, check some of these solutions. This is ON, but this is more than one pass, that's for sure. Yeah, but I'll check those myself, so I will not waste your time. And I'll see you guys tomorrow. Adios.